Hello and welcome to today's Learn at Lunchtime program from the State Museum of Pennsylvania. I am Beth Erickson. Our topic today is Down to Earth, how the Pennsylvania Geological Survey uses satellite data. And with us is Ellen Fuhrs, Senior Geoscientist with the Pennsylvania Department of Conservation and Natural Resources, Bureau of Geological Survey. Her work focuses on the creating and maintaining of a statewide hydrology data set, a digital map showing all the water features in Pennsylvania. The project uses satellite data to help show where the water is, how it moves, and where it's going. Welcome, Ellen, and thank you for joining us today and presenting today's program.
Hi, thank you so much for having me here.
So in a few minutes, you're going to present about the work you do with the Pennsylvania Geological Survey. But before you do, would you tell us about your journey to become a geologist? Were you always interested in geology?
The short answer is no. I was not at all interested in geology when I was younger, but the kinds of things I was interested in astronomy and paleontology and archaeology and communication. And growing up, I kind of found that geology was a way for me to pursue all those different areas. So I love geology. I really think it's the coolest intersection of all the sciences, but there's also quite a lot of communication. And the work I do, it's focused on producing maps and data for maps. And I think there's also a lot of artistry that goes into that. So I love it. I think it covers all my bases.
Well, loving what you do is very important. So let's get started with today's presentation so we can learn more. So Ellen, when you are ready, please begin.
Hi, everybody. As Beth said, my name is Ellen. I'm a geologist with the Pennsylvania Geological Survey, and I'm going to be talking a little bit about satellites today. And kind of how we use the data that come from satellites. So, I wanted to start with some really baseline knowledge just to make sure we're all on the same page. So, what is a satellite? A satellite is basically any object that orbits another body. So for the remainder of this presentation, I'm going to be talking about things that orbit the Earth. So if we look at this definition, a satellite, things that do qualify as satellites include kind of what you'd imagine when you hear the word satellite, like man-made objects that are sent up into orbit to help with things like communication and navigation. But the moon would also count as a satellite. And there's quite a lot of debris that are orbiting the Earth that would technically also count as satellites. So when I say satellites, things that I'm not referring to include things like rockets or spaceships. Aircraft do not count as satellites, and neither do drones, even though we as the Pennsylvania Geological Survey also use a lot of data from these tools. So before I really get into the bulk of my presentation is focused on these man-made satellites that we can use as tools. But I did briefly want to talk about space junk because I think it's really interesting, and just to show you some examples of this. So here is a photo. This is a thermal tarp. This was lost in 1998 during the first space shuttle mission to the International Space Station. I just think it's really interesting to think about all the material that our space missions have led to being put into orbit, some on purpose, some not on purpose. Vanguard 1 is a satellite that was sent up in 1958, and this is currently the oldest man-made object in orbit. I think it's really neat looking. I think it's something like what you would see on Star Trek. And this thing is expected to remain in orbit for 240 years. So a lot of this stuff has longevity when it comes to orbiting the planet. And finally, this is just the result of some space junk. This is an image of a space shuttle Endeavour. So this was an actual spacecraft that was moving people. It was impacted by some debris, and that entry hole you see there, it's about a quarter inch in diameter. The exit hole was about twice that. And that doesn't sound like maybe a huge hole, but when you're looking at a spacecraft that needs to be airtight and is protecting human beings, it's a significant impact. So I just think this is interesting to think about. And one thing I wanted to ask you all as the audience is, how many intentional satellites do you think are currently orbiting the Earth? So by intentional, I mean how many like man-made objects do you think we sent up into space with a purpose? And if you could drop your guesses in the chat, I just think it would be kind of cool to see what you all say. Oh, Elsa said 2000. This is a good guess. I asked this of our interns, by the way, and I had guesses ranging from like 2 to a million. Okay, Lisa says 500. Christopher says 4,800. We got 200, 12,000. I like these guesses. These are good guesses. You guys are all on the right track because it's not a small number. And what I think is kind of interesting is we're not totally sure. So the real answer is you guys are all on the right track. There are thousands of man-made satellites orbiting the Earth. And if you Google this, if you go on the internet and try and find a number, there are a number of websites that tell you different satellite numbers. I think it is incredibly unlikely that any of these numbers are accurate because these satellites are being sent up by government organizations as well as private organizations. So if anyone has a good idea of how many satellites are up in space, it's probably like the federal government, which is far above my pay grade. The other reason I'm kind of skeptical of some of these numbers, if you look at these numbers from Statista, they have like 5,400 in 2022. This website cited like 11,000 in 2023. And then apparently something happened that wiped out over 1,000 satellites, because then in 2024, we're down to like 10,000. So I personally think it's very unlikely that the actual number is publicly available, but we do know that there are an awful lot of satellites orbiting the planet. So having said all that, I am not an astronomer. I'm a geologist. I work for the Geological Survey of Pennsylvania, and I'm going to be talking about how we make use of these instruments. And frankly, the way we make use of these instruments is probably pretty similar to the way a lot of you do, in that we rely on satellites for our global positioning system, or GPS. So this is a satellite system that was put into place by the US government. It was originally put into place specifically for the US military before it was made public. And I like this image I'm showing here, this GIF. If you look at this, it's an image of the Earth, and it's rotating. And all these red lines lead to a single spot on the surface of the Earth. That's Golden, Colorado. And essentially all those red lines connect to these little dots, which represent satellites that are able to see that location. And what I really like about this graphic, first of all, I think a lot of people, when they think of satellites orbiting the Earth, a lot of people kind of imagine them going in this perfect little conga line around the planet, like kind of like the Earth has a hula hoop of satellites, but they're going all over the place in all three dimensions. And what's really cool here, you can see with GPS, this system has constant visibility on every spot at all times. And we use this system to give us locational information. So what I think is really interesting is we're able to get this hyper accurate location information because these satellites are at a known distance from the surface of the planet, and they can constantly see every spot on Earth, and they're able to communicate with instruments on the surface of the Earth. They are also able to communicate with one another. So what do we do with this data? What can you do with GPS data? I'm going to start with the most obvious, which is navigation. And you probably all use Google Earth. I use Google Earth every time I go somewhere new. That is reliant on GPS data. What I think is really cool is that emergency services have made excellent use of GPS data over the years. The first responders especially need to be able to find a location quickly and efficiently, and GPS facilitates that. Services and technology are getting better and better. They're actually getting to the point where if you make a phone call to 911, they're getting to the point where they can locate the building that you've made the call from. They can locate the floor of the building. And pretty soon they're going to be able to locate the room on the floor of the building from which you've made the call. And I just think that's fantastic and amazing. GPS data are also extremely useful for construction projects. They're really useful when you are beginning to plan out a construction project and to understand the scope to which this project is going to require time, effort, resources. And that kind of leads into infrastructure maintenance. So there are a lot of construction projects related to infrastructure that rely on GPS data. So if you are familiar with the PennDOT road closure system, anytime a road is closed and they have to provide an alternate route, the goal is to use GPS to create the most efficient detour that they can. But none of this is geology. So I do want to touch on what we do at the Pennsylvania Geological Survey. Again, this is where I work. The Pennsylvania Geological Survey is divided into 3 divisions, including geologic mapping, geologic resources, and geologic and geographic information systems. So geologic mapping, that's largely the field work where our geologists go out into the world. They find rock exposures, make interpretations, collect data, and make interpretations based on that. Geologic resources includes things like subsurface geology. So if we have to drill a really deep well to understand what's going on underneath the surface of the earth, or if we have to do geochemical analyses, this would fall under our geologic resources division. The Geologic and Geographic Information Services division is the division I work in, and this is a lot of map making. So this division involves taking data from the other 2 divisions and trying to produce a usable product, essentially. And all 3 of these divisions rely heavily on GPS and satellite data. So every map that we publish as the survey uses satellite data. And some of you might be familiar with our website, PAGeode, or the Pennsylvania Geologic Exploration Tool. This is something I'm going to be talking about later, but this is where you can access all of our publications. So these maps show things like where specific rock types are, where specific geologic hazards may occur, where water flows and collects, and where you can find individual geologic resources. So when we do this work to prepare for some of these products, the first step is usually something like field work. And GPS is really important to our field mappers because the number one reason is for safety. Our mappers go into some very remote parts of Pennsylvania, and they need to have an accurate idea of where they are. We don't want them getting lost in the woods. That would be very, very bad. We also want them to constantly be aware of where they are so they don't accidentally wander on to private property. Or if they need to access private property, they need to know where those property lines are so they can ask permission to access that area. Now, another aspect of fieldwork, I mentioned this earlier, is data collection. So we collect data in a number of different ways. One of the biggest ways is sample collection. We will collect rock samples. Like this first photo is from one of our interns, Shafia. She was collecting these rock samples. We collect water samples, like my coworker Victoria is demonstrating over here. She is collecting water for geochemical analysis from a spring. We also take measurements. The photo in the center shows my coworker Aaron. He's taking some structural measurements at a site. But all of this data, all of this information is completely useless if we don't have locational information to tie it to. So that is where GPS comes in. Now, historically, we have relied on these Garmin GPS units I'm showing on the left-hand side. Essentially, what we would do, we'd have that handheld unit go out into the field, find a rock exposure, maybe we collect a sample, maybe we take a measurement, and then we record that point, go back to the office and plug that unit into our computer and upload all the data onto the computer so we can share it with everybody. But more and more so, we are moving away from these traditional handheld units and towards iPads, which if you look at the image in the center, that's my coworker, Chris. He is taking some data collection on an iPad. And I'm showing a picture on the far right of my iPad, just showing a demo map. So the nice thing about these iPads is that they are constantly connected to the cloud. So as our field workers go out in the field and they collect these data are instantly being shared with people back in the office. So I am able to sit at my computer in the office and watch and interact with these data points as they're being collected. And if the people in the field need new data provided or they need some kind of information provided, I can send that back to them in real time. And the nice thing, because since all this is happening on the cloud, there's no manual upload component. So our field workers don't have to come back to the office and physically plug the GPS unit into the computer. It's just automatically being archived online. So what's really nice about this as well is that it makes it easy to combine these GPS data with remote sensing. And honestly, this presentation probably should have been called Remote Sensing at the Survey, but I didn't know that everybody would know what remote sensing is. So remote sensing is data collected from satellites or aircrafts without any kind of a field component. So any image you see of the Earth or of another planet, those count as remotely sensed data. And I wanted to show you guys some examples of data that I'm a little bit more familiar with. So this is imagery that was collected from an aircraft. I don't think it was collected from a satellite. I think it was from like an airplane flyover. But this is showing downtown Harrisburg in 2004. You can actually see there's some kind of artifact going on with the State Museum. There's some weird little echo going on. And if you look at this image, I think it's interesting because a lot of people might look at this image and look at these trees and see how red they are. Your first thought may be, oh, was this collected in the fall? But if you look at it carefully, you can see there are areas where we would expect to see grass or expect to see greenery that are also red. So looking at this, I know that this is a false color image. So sometimes these images are given kind of a false color filter in order to make specific features more noticeable. And as we go through the years, you can see, okay, we've lost the false color in this image, and we can see that the image is getting slightly better. The resolution is improving. And that is something you would expect to see if you are comparing images throughout a number of years. And what I think is really cool, as we continue to go through the years, you can see the angle at which these images were collected is changing slightly. You can see buildings start to tilt in a different direction, and that's just based on where the aircraft was when it collected this image. Another thing you may notice, if you pay attention to the shadows, is that these images were collected at different times of the day. And continuing to compare them, the shadows might change direction, they might increase or decrease in length. So I think it's pretty interesting. And this site in particular, I don't see a ton of urban development because it's already been pretty well developed. But if you're interested, you can access some of this imagery through PAGeode, and I'm going to show you how to do that at the end of this presentation. Okay, so that imagery can be extremely useful. When I was in school, I went to school in Colorado, And in Colorado, the geology looks a lot like this. They have these big, beautiful rock exposures. And when you have geology like this, remote sensing and satellite imagery can be very useful. However, I do not live in Colorado anymore. I'm in Pennsylvania, and imagery isn't as useful for the type of geology that we're studying in Pennsylvania. And in fact, the US Department of Agriculture released a statistic for 2020. Pennsylvania is estimated to have about 60% forest cover. And that is very different from Colorado. I think Colorado's estimate is something like 30% forested. So a lot of the geology, a lot of the rocks we have in Pennsylvania aren't exposed at the surface. They're covered by vegetation. So we as geologists don't rely on imagery as much as we do other types of remotely sensed data. And the kind of remotely sensed data that I work with the most is something called LIDAR. LIDAR is an acronym for light detection and radiation. Oh gosh, I messed up the acronym. But essentially, LIDAR is described as radar with lasers. And what we have here on the left, this is an image of Hershey Park. On the right, this is a LIDAR hillshade. So it's in black and white. It is depicting an elevation surface of the park. And you can see it doesn't have any color information, but this shows the elevation essentially of all these different features. So we can still see the bare earth. We can see all these little trees lined up. We can see some of these buildings, some of these roller coasters. But the really nice thing about LIDAR compared with to traditional imagery is that LIDAR has the ability to penetrate some of these materials. So if we want to, we can actually strip back some of that information and expose an approximation of the bare earth surface. And this is the kind of information that I typically work with. Okay, so to give you a little bit of background, LIDAR instruments can be mounted to satellites, but they're very versatile. They can also be mounted to airplanes. They can be flown with drones, and I've read about them being mounted to cars. Now, cars, that's definitely not as common because it's a lot more efficient to cover a large area with like an airplane flight compared to driving your car manually over it. But cars can sometimes use LIDAR instruments, particularly if they're trying to analyze what roads need to be repaved or where there's been extensive damage to road systems. So the way this instrument works, if you have some kind of mode of transportation, in this case, I'm just showing an airplane, but if you have an aircraft that has a LIDAR instrument on board, the instrument will send down a laser to the surface of the Earth. This laser is able to penetrate certain materials, but as it penetrates the materials, like if we look at this, as this laser comes down and strikes this tree, every time it strikes the surface, it will send back a small pulse of energy. So when it hits the surface of these leaves, it's going to send back a little pulse of energy. When it hits the trunk, it's going to send back another pulse of energy. And finally, when it hits the surface of the Earth, it's going to send this last return of energy. So the sensor, the instrument on board, is a known distance from the center of the Earth, from the surface of the Earth. So the instrument is able to make an interpretation based on how much time these pulses of energy take to return. It's able to interpret how far away these surfaces are from the sensor. So that's how it's able to create these elevation surfaces. And I wanted to show you guys an example because I work primarily producing hydrography, which essentially that's just maps showing where water is likely to flow, where water features are. And if I had to rely solely on traditional imagery, if you look at this, looking at this image, if I had to pick out all the water features, I think I would struggle a lot. I can see there is this one kind of stream feature going like east-west towards the top of the image, but beyond that, I'm not really certain. But if we look at the LiDAR with all that vegetation stripped away, it becomes a lot easier to see what are probably stream channels. So these are the data that I use to produce hydrography. And these orange lines are kind of the flow paths I've modeled based on the LiDAR data available. So I just wanted to show you one more example of that. This is another example looking at this image. I just using this image, I don't think I could do a very good job producing hydrography, but having a LiDAR surface makes it a lot easier to pick out where some of these channels occur. And from that, we can produce some really accurate, up-to-date data. So that is what I work on. But at our survey, another thing that we pay a lot of attention to are geohazards. And LiDAR can be extremely useful in identifying these hazards and giving us information about these hazards. So here's an example I wanted to touch on with landslides. The images you see on this slide, these are from a project I did with my coworker, Helen Delano. She has since retired, but she and I co-authored a poster with a few other people looking at a specific landslide feature in the Pittsburgh area. So that's where these photos are from. And if you look at this LiDAR image, you can see, okay, so looking at this, these linear features are roads. You can see some of these rectangles, those are building footprints. And this down here is kind of part of a forested area. But if you look, there's this kind of weird funnel-shaped feature. That is where a landslide occurred. So these two images were actually taken up here, kind of at the head of the landslide. And so what we did for this poster is we took two sets of LiDAR data, and one set was from a year before the landslide, and one set was from a year after the landslide. And we subtracted one from the other because the biggest changes in elevation should be indicative of like major development, like either a new building or something like a landslide. So that helped us significantly when we were trying to determine the extent of this landslide and characterize it. And something I thought was also really cool, these colors I'm showing over the LiDAR image, the colors represent different values from when we subtracted those two elevation layers. But there's also the secondary feature that's kind of starting to pop out. And what I think is so neat about this is helping us characterize a second landslide lobe. But if you were there in Pittsburgh, standing at the top of this ridge, the damage from this larger landslide is very obvious. It's what you see in these images. But what was going on over here with the smaller secondary landslide was a lot less obvious. And it may be something that you wouldn't even notice, even if you were standing there in person. So LiDAR helped a lot with identifying aspects of this hazard. And if you are interested in learning more about landslides, I have a coworker, Stephanie Evans. She is specializing in landslide studies, and she is working on compiling a landslide database for the state of Pennsylvania. Now, another hazard that we are particularly concerned about in central Pennsylvania are karst hazards. So this includes things like sinkholes, caves, and depressions. And what I'm showing here on the right, this is a map I assisted my coworker, Rosanna Bear, with. She took LiDAR, and based on her knowledge of the underlying rock type, like the underlying geology, and using LiDAR to characterize surface drainage, she made a prediction about where karst features are most likely to occur in Mifflin County. So first of all, I do want to say this is a statistical tool. She didn't go out in the field and perform geophysical tests to see whether karst features were likely to occur in specific spots. But this is a really good tool if you live in Mifflin County and you are interested in finding out more about kind of how karst hazards could be dispersed throughout the county. And this is something that she hopes to continue doing for all the individual counties. So if you are interested in learning more about karst studies, Rosanna Bear actually presented last month for this same educational series, and she was talking about caves. So I would also encourage you to reach out to Rosanna. And this brings me kind of to the end of my presentation, but I would like to talk about how you can use some of our products. And I just saw a question in the chat. Could we get a copy of some of these posters? Absolutely. I'm going to show you how to do that right now. So all our publications are available through our application PA Geode. And I am going to drop that link in the chat right now. So if you want to follow along with me right now, you are welcome to do so. But if you want to access any of the posters or the maps or any of the reports I referenced in this presentation, I encourage you to check out PA Geode. And I'm going to walk you through it right now, but if you have any questions after the fact, you are always welcome to reach out to me through the email that was provided with this presentation. Okay, so this is PA Geode. When you first log on, it's going to look something like this. This navigation plane might not be expanded when you first get to the website, so you might want to pop that out. And this just shows the different data types and the different, like, whatever you are interested in looking up on this website, right? So looking at this website, let's say I want to find Rosanna's map on karst hazard prediction. Okay, I know it was for Mifflin County, but looking at this map, maybe I don't know exactly where Mifflin County is. I know it's kind of in the center of the state, but maybe this base map doesn't give me enough information. So if you want, you can come up here, this top icon in the upper right-hand corner. This has options for different types of base maps, and they have a lot of options. And I mentioned earlier when I was talking about imagery that you could access different imagery on PA Geode. This is where you would do that. So if you want to go in here and look at maybe imagery from 2015, you can select that, do that. It might take a moment to load. Imagery takes a long time to load, especially because I'm sharing my screen. So I'm actually going to maybe not do that. But what I am going to do is switch to a base map that I know has county information. Okay, and as you zoom in, the screen is going to be populated with more and more information. And you might get this little warning. I wouldn't worry too much about it. But looking around here, okay, we can see Center County. Zoom out a little bit. Where's Mifflin? I'm going to look bad if I can't find Mifflin. Okay, well, maybe I can't find Mifflin right off the bat, but I know I want that map. So I'm going to come over here to publication search. So this is going to have all the publications from the Pennsylvania Geological Survey. The current survey, the one I work for, is the 4th survey. I know I am interested in a map, so I don't quite know where I'm looking, but I'm just going to draw a big rectangle and see what's returned for this search. So looking here, these maps are in order of publication, and I know the Mifflin County report was pretty recent, so I'm going to zoom to the very end. Here we go, karst feature density map of Mifflin County. So then you would come over here to the open link, and it would bring you to a data landing page for whatever project you link to. It's going to have a short abstract. It's going to have the title and a representative image. You would go ahead and download it. And once you do that, and in fact, I'm going to share this link in the chat just in case any of you want to look at Rosanna's karst map. But once you do that, you are going to get a downloaded zip file. If you open it up, it's going to have some GIS data if you want to get fancy with the tech. Or if you just want to look at a PDF of the map, you double click that. And here we have Rosanna's map. And I think this is the coolest map. She explains in detail everything she did when it came to modeling these karst features. I thought I saw, I'm going to open it up to questions right now, if anyone has any questions.
All right. That was terrific. Thank you so much. I know for me personally, viewing the museum and Capitol complex from above it's such a different view that we don't think of as humans who are earthbound and walking. So that was terrific. So, all right, a couple questions. So would any of this be useful to find areas, likely areas for fossil-bearing rock?
Yes, so there are known lithologies that host a lot of fossils, particularly in Pennsylvania. When I think of fossil hunting sites, I think of the Devonian with a lot of marine fossils. Another thing I might direct you to, we have an educational series, and if you don't mind, I'm going to look it up as I'm talking. But this educational series has a pamphlet on fossil hunting in Pennsylvania, and I very much encourage you to check it out. Do we have any other questions?
Yes, there are a few. So while you're doing that, so what about coal mines? Are there maps for coal mines?
Oh, we have so many maps for coal mines, definitely. And in fact, I'm going to drop a link in the chat for our educational series. In addition to a pamphlet on fossil collecting in Pennsylvania, we also have a pamphlet on coal resources in Pennsylvania.
So how accurate is the GPS technology that's used in the survey?
At the survey, the units we use, they actually give you an estimated accuracy, and that can change when you're in the field depending on where you're located, depending on ambient conditions. If there's really heavy cloud cover, that could potentially affect your accuracy, but generally it's around 6 feet.
And how long would satellites last if humans did not exist any longer?
Oh, that's a good question. I think some of them would just plummet out of the sky. Not that they'd strike the earth. Most of them, I think, would burn up in the atmosphere. But when I was talking about space junk and I showed that tarp that disconnected from a shuttle and was kind of floating off, that did orbit for a few days, but then it fell out of orbit. So some of them, that's a really good question. Some of them I think could last hundreds of years. Some of them I think would fall out of orbit pretty quickly.
Are there also maps for natural gas wells?
There are. I'm trying to think the best way to access those. Off the top of my head, I'd have to look around on PA Geode, but we do have information for gas wells. We also have information for water wells. But that is something I would encourage you to reach out to the survey through either me, and I would put you in contact with somebody in our geologic resources section, or just reach out to them directly. But they could provide you with maps showing the location of gas wells.
Does any of the sun activity, solar flares or storms, affect the satellites?
They can, certainly. For the record, the way I interact with satellite data, I probably wouldn't even know that a blip in the data is the result of a solar flare until maybe days after it happened. So it's not something I experience regularly working with the data that I use.
Someone noticed gold in Colorado in one of the graphics.
Yes.
Yes, what was the reason for that being included?
Oh, I just thought it was a really cool graphic showing how satellites interact with one another, well, how satellites send and receive information. So it wasn't, I didn't choose that graphic because it was Golden, Colorado. I chose it because I thought it did a good job showing the dispersion of satellites in orbit. And the reason it shows Golden, Colorado is the person who created that graphic is from Golden, Colorado.
Oh, there you go. Nothing against Golden, Colorado. It's just not
No,
Pennsylvania.
I went to school in Golden, Colorado. I think it's a neat place, but Pennsylvania is the best. I am so happy to
Definitely,
be
yes.
back. Mhm.
So, what's your favorite type of remote sensing technology?
There are some really cool types of remote sensing technology. I think LiDAR that I showed in this presentation, I think it's one of the coolest. You can do so much with it. But a kind of remote sensing technology that I haven't used regularly is hyperspectral remote sensing. So there are satellites that with instruments that are able to essentially collect imagery, and based on the spectral signature they receive, they can make interpretations about the mineralogy of the surface of the planet. Now, that only works when you have exposed rock, but that's something that I've read that astronomers use extensively with things like with bodies like the moon and other planets, where the surface of the planet isn't covered by a lot of vegetation. And I always just thought that was so cool.
Well, I want to thank everyone for your questions. Ellen, what would you like the audience to remember from today's presentation?
The big thing I want you to remember is that these types of data are incredibly useful in a lot of ways, and they're very accessible to you. I want to empower all of you to take advantage of the resources that exist and learn about some of these data and learn how you can use them to whatever you want to do in life. If you want to purchase a house in an area that has a low likelihood of karst hazards, I want you to be empowered to do so.
Please join us again for more Learn at Lunchtime programs. Visit the State Museum of Pennsylvania's website at statemuseumpa.org for program information and to sign up.